Our next speaker is Marina David, and she will talk about holographic approaches to ADA's black hole entropy. So thank you very much, Marina.
Okay, so first I'd like to thank the organizers for inviting me to give to talk today about some of my recent work with Leopoldo Pandozayas, who is in the audience and my advisor, and Jun Lian, who is now at ICTP in Southeast Asia. Holography has given us a very clear computational path to compute some, to give us some ways to answer some questions, including understanding how to relate the microscopic and microscopic origin of black hole entropy. So our story starts with back in '96 by Strominger and Vafa, who successfully computed an asymptotically flat, the entropy of a flat black hole entropy. And later, this was expanded for asymptotically ADS because of holography by computing the index. So some of this will be a little bit from Alejandro's talk. So I'll spare you some of the details. And so looking at the index, Kini Maldacena, Manuel, and Raju, back a decade after the first success of Strominger and Vafa, computed the index. And unfortunately, it was not a success, more so because of the scaling. So if you look at the index and look at the large n limit, you'll find that it is of order 1, whereas the black hole entropy, which scales as n squared, is not of order 1. So there is some mismatch in scalings, and there is some, and so this cannot reproduce the entropy. But recently, a few years ago, there has been some success in actually computing this correctly by 3 groups here, using beta onsets approaches, supersymmetric localization, and the one that I will focus on in this talk is the Cardy-like limit. And the key insight in this particular case for these 3 papers was to allow for complex chemical potentials. So just to give you a little bit of an overview about what the Cardy limit is, consider just a 2-dimensional CFT. And in the thermodynamic of the CFT, we'll say that the central charge is much less than the energy. And this is typically the limit that is enough for us to determine the entropy of the system. So the Cardy-like limit is similar, and we take the chemical potential, which is associated to the rotation, to be quite small. So giving this a little bit of story and background, our work was try to answer the following questions. So first, what is the underlying principle of this Cardy-like limit that was successful in computing the black hole entropy in ADS5 and later in other dimensions? Can extremality be relaxed? So all of these black holes were in the supersymmetric and extremal limit. So our question is, can extremality be relaxed? And I'll explain a little bit more about extremal black holes. How much can we uncover about the black hole without knowing the full UV description? A lot of the times, these black hole solutions are very difficult to find, and trying to understand some information about the black hole without knowing the full solution is quite useful. More importantly, also, is learning about the parameter space and what we can learn about understanding the space of all solutions. And I'll do this by answering these questions by understanding and learning about the Cardy-like limit on the gravity side, and also focusing on both extremal and non-extremal black holes. So in case you're really excited about the results, here it is. So I like to show this picture because it really gives an overview of what we've done in our papers. So consider some black hole in ADS-B plus 1 dimension. So we've studied a class of rotating asymptotically ADS black holes. And we know that we can compute the Bekenstein-Hawking entropy, and so this is called S1. And because of holography, we have ADS CFT, and we can look at the boundary CFT. which has been successful in computing the microscopic entropy. On the other side of gravity, so if we go back to gravity and consider the near horizon region, we get an ADS3-like geometry because we have some U1 fibered over the ADS2 because we have rotating black holes. And ADS3 geometry is really nice because we can use another holographic approach called Kerr CFT, the Kerr CFT Correspondence, which relates some ADS3 geometry to a CFT2. And we can compute yet again the black hole entropy, which I'll call S3 here. And we'll find that S1 and S2 and S3 gives us the same results. So you can just pick, the one that is convenient to you if you would like to compute the entropy. So a visualization, though, of when I say Kerr CFT and asymptotics and the horizon is this following picture that I like to show. So when I'm talking about the horizon, I'm talking about near the throat of the ADS2 region. And this is also where the beginning of Kerr CFT starts. Whereas when I talk about the CFT or the asymptotics, I'm in the outside region all the way out to the boundary. So I'm right here. I did mention extremality a little bit, but I just want to make sure that just to review the definition of extremality. So with these black holes, we usually have two horizons, the inner horizon and the outer horizon, R plus and R minus. And when they coincide is when we have an extremal black hole. So typically you'll solve this function f, you'll find R plus and R minus, and when R plus equals R minus, then that's when you'll have extremality. This is also the limit where the black hole temperature is 0. So this is also very important. And so when we talk about extremality and supersymmetry in this talk, both limits just for me is going to be UBS. However, sometimes this is not enough when I want to say I want an extremal black hole solution, because sometimes we have to look at if the solution is physical or not. So there can be closed time-like curves, there could be naked singularities, and sometimes that we will have to restrict our parameter space further so that all our solutions that we're looking at are physical. So these are the black hole solutions we studied in our papers. There are obviously many more papers and many black hole solutions. The ones that I have underlined are the ones I'm going to focus on in this talk. Although, like I said, there are many more. So we're going to start with the ADS5 black hole solution, and then we'll later go on and look at ADS4. So for the ADS5 black hole solution, just to give you a sense of what it looks like, I wrote here the metric and the gauge potential. And more importantly, we want to look at the parameter space. So the solution is parameterized by 4 quantities, A, B, M, and Q. So A and B characterize the rotation. So in this case, there are 2 rotations. M is corresponding to the mass, and Q corresponds to the charge. For simplicity, we set Newton's constant to 1. And this parameter G here is just inverse, is 1 over the length scale of ADS space. I don't think it's written here, but you'll see it in the later slides. And we also have chemical potentials. You have Q and omega corresponding to the charges in our solution. So, like I mentioned, we are interested in supersymmetric solutions. The supersymmetric condition ends up giving us a constraint on our parameters. So we had 4 parameter family of solutions, and now when we apply this constraint, we'll have a 3 parameter family of solutions. This solution for ADS5 also has closed time-like curves. So one possible solution to remove these unphysical solutions is to consider a supersymmetric solution along with this additional constraint on the parameter corresponding to the mass. So now we have our family of solutions have become now just two family parameter solutions, A and B. So to give you a sense of what the solution looks like, and when I talk about extremality and supersymmetry, I like to just look at the plots of the extremal and supersymmetric surfaces. And you'll see here that the supersymmetric surface is below the extremal surface. That means, and any solutions that are below this surface, this green surface here, will be corresponding to unphysical solutions. So that means that I could not have, in this particular solution, I could not have a supersymmetric non-extremal solution because this will be unphysical and will be below the green surface here. However, like I mentioned, we're actually imposing an additional constraint to remove the closed time-like curves. And then you see a very clear intersection of the extremal surface and the supersymmetric surface. And this line here are what I call the BPS solutions. And this is the solutions that we are seeking in this particular with the Cardy-like limits. So these are the solutions we will be studying along with the Cardy-like limit. Okay, so back to the Cardy-like limit. So the limit proposes that omega, which is of order of epsilon, so very small. And what we'll do is we'll demand that in the entropy function, that every term in the entropy function is going to correspond to the same order in epsilon. So this will vary a little bit in dimension, but we'll focus here on 4 dimensions since we're looking at ADS5, and we'll see that the entropy function is going to be 1 over epsilon squared. So if we can find a corresponding Cardy-like limit and also find that the entropy goes as 1 over epsilon squared, then I would say we are in very good shape. So again, here's the Cardy-like limit, and it has been shown by that omega can be related to the temperature derivative of the angular velocity, and then at extremality. So now that we have some corresponding relation between the CFT parameter and the ADS parameter, we can now try to find a corresponding Cardy-like limit on the gravity side. So we'll do just that. So when we translate the Cardy-like limit, we'll impose the value of omega, and we'll then take the temperature to 0, and we'll find this constraint here. And so if we want this to be very small, we will require that A goes as 1 over G, or in other words, since G is 1 over the length scale of ADS, A has to be L, which is the length scale of ADS. So the Cardy-like limit then is going to be imply that a very special limit on the parameter space, and particularly that A and B are very large. And since we don't want exactly 0, since omega is of order epsilon, we'll take A and B to be also 1 over G minus epsilon. So the Cardy-like limit on the gravity side, so the gravitational Cardy-like limit, is some black hole with very large angular momentum and charge. And so our gravity translation of the Cardy-like limit ends up being just some particular limit on our parameter space. And in all the cases that we studied, whether it's ADS5 or ADS6 or 4 or 7, we found a similar limit on the Cardy limit, that A, which is related to the rotation, times G has to be much less than 1. So again, it is valid for all dimensions. So now I can take this gravitational Cardy-like limit and impose them on the thermodynamic quantities to see if the scaling that we expect is indeed on the gravity side. And like I mentioned, the entropy is 1 over epsilon squared, and you can see here that when we impose the Cardy-like limit, you do get 1 over epsilon squared on for the Bekenstein-Hawking entropy. So this is the precise scalings that we find on the field theory side. Okay, so again, here's our main results, and essentially what we did here is this gray square here. So we looked at S1 and we looked at the Bekenstein-Hawking entropy with the Cardy limit imposed. So now our next step is to actually go down here and try to understand this other side by taking the near horizon solution. So our approach then will be to study the near horizon solution following in a co-rotating frame. So R0 here is the horizon of the black hole, particularly at extremality. So R plus equals RH. And we take lambda to 0. So just a comment that the near horizon does indeed satisfy the equations of motion. And we will now apply this scaling, this near horizon scaling, and the gravitational Cardy limit to see if we can, to study the geometry there. And so the near horizon takes this form. So it has some ADS2 factor, and it has two circles fibered over the ADS2 because you have this RDT. And this B0 and C0 are some constants, but this F, V, and D and lambda are some functions of theta. So in both of these circles, you'll see that, although I didn't write it, you'll see from the expressions that C and V are proportional to the time derivative of omega, or the temperature derivative of omega, really showing that the angular velocities are slowing down on these U1 cycles in the near horizon geometry. And indeed that they play a role in the angular velocities in the metric. So now that we understand the ADS3 geometry, now we can move on and use holography one more time to look at the CFT2. So what is the Kerr CFT correspondence? The Kerr CFT correspondence starts with some
Marina,
yes.
may I interrupt you?
Of course.
So what happened to, so if I didn't misunderstand in the previous transparency, you took
This one?
exactly, yeah. You took this limit and you will construct an ADS3 because of these vibrations over ADS2, etc., right?
Yes, exactly.
What happens to the rest of the space? By which I mean, suppose that you have an ADS5 or higher ADS times something, say you put it in type 2. What happens when you take this Horowitz-Bardeen limit with the rest of the space? I understand how you construct the ADS3.
So I have imposed, I mean, the list limit is imposed on the entire metric, not just focusing on this, on the U1 and ADS2 part. Am I understanding your question correctly?
Oh, okay. So I see you have two directions.
So
one more in phi, one more in theta.
All of these are the
okay. So this
near
is
horizon limit.
This
is the full near horizon solution. Yes.
Okay.
With some details omitted, but yes.
Good.
Okay, so now that we have the ADS3, then we can go back and use holography once more and use Kerr CFT. So the Kerr CFT correspondence starts with some ADS3 geometry, which is why we took the near horizon limit to begin with. The Kerr CFT correspondence was first studied by Strominger and collaborators in 2008, and then was later extended for asymptotically ADS black holes sometime later. And what the idea is that once you go to the near horizon and you get some ADS3 like geometry, then by studying the asymptotic symmetries in this near horizon region, you'll find that a Virasoro algebra emerges with some central charge, and that central charge precisely reproduces the entropy that you're seeking. And so this microscopic computation has been computed for numerous black hole solutions, and our goal now is to study the Kerr CFT correspondence with this Cardy-like limit. So, we'll first use the Cardy formula, which is part of the Kerr CFT correspondence, part of the prescription, and it requires two things we need to compute. So the central charge and this Forloff-Thorne temperature, which is called TL here. There's also technically another term, which is CRTR, and TR is proportional to the Hawking radiation. So at BPS, TR is going to be 0, and so there's only actually really one term we need to compute. So at non-extremal, we will need to compute an additional term. So if you compute the central charge and temperature following the Kerr CFT correspondence, you will find these four corresponding expressions, and then you apply the Cardy formula. And you find this black hole, this to be the entropy. Now, however, we want to now compute it by imposing also the Cardy-like limit. So when you impose this gravitational Cardy-like limit, the central charge and the temperature are both order 1 over epsilon, and so the entropy is going to be 1 over epsilon squared, as predicted from my previous slide with that table. So this precisely matches the result that we had found before. You may not remember the coefficients, but they're exactly the numerical coefficients we also were seeking. And so now finally, we have computed this last corner here of our diagram. So now we can ask, so let me recap first. So first we've translated this Cardy-like limit from field theory to the gravitational Cardy-like limit. And we were able to reproduce the entropy both via Kerr CFT and Kerr CFT, computing the central charges and computing the left temperatures. Kerr CFT is one component of this computation and one part of this diagram I had shown. And we find that this Cardy-like limit and its corresponding gravitational Cardy-like limit is just some scaling on the parameter space, and it produces the scaling to numerical coefficients we expect. And we get one universal result regardless of the method we choose. Given some ADS black hole solution, we choose the method we prefer, and we'll get the same entropy. And now we can relax the Cardy-like limit and extremality. So in this section of my talk, I'm going to just talk about ADS4, the ADS4 black hole solution. And again, I'll show you the plot, a similar plot to the one I showed for ADS5, but this one is for ADS4. A here is the rotation. And delta 1 is the parameter corresponding to the charge. The yellow here, the yellow plot, surface, excuse me, is the extremal surface, and the green one is the supersymmetric surface. So what's interesting in this case is that because of the way they look, we can have a supersymmetric solution on this surface here that is also at extreme, that's non-extremal. Whereas in the other case, the parameter space gave us a different result. Recall that all the solutions below here are going to be unphysical. So what we define to be the near-extremal solution is going to be a supersymmetric solution because I'm going to be on this surface, but I'm going to be above the yellow surface. So this is what we define as near-extremal. Because we are going to be near-extremal, the temperature, instead of being 0, it's going to be very small. And some of this work for near-extremal black holes has been studied by Larson and collaborators. And the result that we will find, which also matches their result, is that the entropy, is going to be the BBS entropy, this term, and then an additional term that's proportional to the heat capacity of the black hole times the Hawking temperature. So we expected for a near extremality that this expression here, this extra term here, is going to be small because we have very small temperature. And so by focusing on the ADS4 case, there are 3 different approaches we can take. So the first one is to just expand the Bekenstein-Hawking entropy around its non-extremal solution, but for small temperature. The second method is to use Kerr CFT once more, but extend it to the near-extremal case. And the third method is to try to look at the boundary field theory, which is in this case ABGM, and at small temperature look at the microstate counting and see if we can reproduce the entropy. And so this works. And to spare you some of the details, we still find that this diagram is consistent. So for both near extremality, BPS, and the Cardy-like limits. Okay, so just to give a little bit of concluding remarks and future directions. So in all of solutions that we solved for and we studied, they were rotating black hole solutions. And so the near horizon geometry was always some U1 fibered over ADS2. And we used this to understand what the Cardy-like limit meant on the gravity side, which was we called the gravitational Cardy limit. We also did find consistency of the entropy regardless of the method, also showing and understanding that holography indeed works here. And there is some universal entropy regardless of the approach. We also were able to translate the Cardy-like limit to some parameter space limits, and we were able to understand the parameter space in depth. So from future outlooks is, well, near extremality was only done for some dimensions, but And in certain cases, it would be interesting to understand near-extremality in other cases as well, and maybe define near-extremality in a more rigid way. And extending on that too, instead of near-extremality, what about far from extremality? Unfortunately, holography does not help too much in this case. And we don't have a lot of tools in the non-extremal regime. And finally, some extensions of asymptotic symmetries in Kerr CFT. So there has been some work looking at the near horizon region and understanding the conserved charges at the near horizon, which is different than the Kerr CFT, which extends out to infinity after imposing the near horizon solution. So understanding these extensions and these regimes and where we can understand where the conserved charges come from would be also very interesting. So with that, I will conclude. And if you have any questions, please feel free to ask.
Thank you for a very nice